Hi everyone, I'm David Aboud. Welcome to today's webinar dedicated to using the gloss and retrace tools for better traces on your circuit boards. We're going to do things a little bit differently today since we're all working remote here at Altium. The presentation and demonstration will be recorded, followed by a live Q&A. I will be starting poll questions throughout the presentation to learn more about your needs. If you have any questions, please put them in the Q&A section, and if there are any issues, please put them in the chat section. Okay, let's get started. As part of the webinar, we're going to start by looking at the major trends in the development of electronics. Then we're going to discuss the basics of signal integrity and list the basic requirements for traces in terms of better signal quality and the technology for the production of the PCB. After that, I'll talk about the gloss and retrace tools and show you some live examples of their use on the circuit board. The constant increase in data transmission speed brings new problems which each developer must solve during the PCB design cycle. You know, the signal quality of many PCB elements are not affected at lower speeds, but they begin to experience a negative influence as speed increases, smoothly transferring a PCB into non-operational condition. It's not an uncommon case for a PCB to be made and assembled without errors, but the required functionality of some high-speed interface does not work properly due to the problems with signal quality. The main problem is that as the interface of the speed increases, all negative features of the topology begin to have a stronger impact on signal quality. And to implement modern technologies in your PCBs, you need to pay attention to the quality of the routing. The requirements for tracks can be separated into two related scopes. First, the signal integrity scope and the manufacturing technology scope. The first requirement is the exclusion of sharp corners from track routing. This requirement is both topological and technological. Also, the track should have a minimum number of different bends and, if possible, have no stubs. This will be explained in more detail later in this webinar. Differential pairs should also be symmetrical to each other and have no irregularity in the track's path. All of these requirements are subject to the technological requirements for clearances and track width values, and these are limited by the factory of your PCB manufacturer. Let me remind you that we're talking about the basic requirements for tracks. So this will allow you to avoid problems with signal quality and PCB production in most cases. In the following sections, we'll consider these requirements in more detail. But before we move on, I want to briefly touch on the fact that due to the increased speeds we see in PCBs these days, our traces are acting as transmission lines. So after this webinar, I recommend you watch the transmission line impedance webinar to learn more about some of the use cases where the gloss and retrace functionality will really help you out. Now let's talk about the basic concept of signal integrity. Signal integrity is the presence of sufficient data in the signal, right? So this is the point at which it is possible to transmit the signal over a certain distance without errors. So developers of digital signals tend to idealize the signal and present it as a rectangular or trapezoidal form. So let's take a look at the picture above. The top part of the drawing shows the idealized signal in most cases that is imagined by the PCB designer. The signal has certain thresholds for setting a logical 0 and a 1, allowing the whole digital electronics to operate. However, real signals might look quite different while the system is operating. In the real world, there are no ideal signals, and because of several reasons, the digital signal is distorted from the ideal form, and there are errors in signal transferring. Ensuring signal integrity comes down to actions that bring the real signal closer in form to the ideal one. To check the quality of the signal, an eye diagram with the rise, holding, and fall levels is usually used. The signal should not go beyond the specified thresholds and should not be superimposed on them. If the signal does not comply with the requirements of the eye diagram, communication errors occur during the operation of this signal and under these topological conditions. The parameter values for eye diagrams are specified in the requirements for each speed standard. Okay, so there are three fundamental approaches to solving problems of signal integrity. The first approach is to change the technology used on the PCB. So, for example, you can change the IC to a slower one. The second approach is to change the topology. So we're talking about changing the routing style, reducing the track length, and adjusting the track geometry. And the third approach, we're talking about termination. So that's matching the traces so that they don't contain any errors, matching the components, the entry points on pads and things like that. So it's really important. The PCB trace has a strong influence on signal quality. So when we consider the basic requirements to traces, these are all going to allow minimizing problems connected with decreasing signal quality. So we're also going to list some of the recommended rules to adhere to for every engineer and designer. So let's look at the actual requirements for traces in terms of signal integrity. So the first requirement we're going to talk about is excluding sharp and right angles from signal routing. So when we are analyzing this requirement, we're going to first look at it in the scope of signal integrity. When we are routing a track in this manner, what we have is an effect called signal ringing. You can see an image down there. This effect occurs because after setting the logical threshold, the current of the signal is not setting at a required level, but moves at a certain amplitude, which leads to false switching. So to reduce the ringing of high-speed tracks, it's recommended to place them at an angle of 45 degrees, or you can completely round off the bending area. Now let's look at this requirement in terms of manufacturing technology. So with this kind of routing, sharp angles can lead to an acid trap effect on the PCB. So this is going to negatively affect its reliability and also etch excess copper. Also, in the presence of sharp angles in the bending area, residues of chemical materials used in production may remain. So over time, this can lead to peeling of the foil, which we refer to as delamination. So to avoid such problems, track angles should be routed at 45 and 135 degrees, or they should be rounded. So newer etching techniques reduce the probability of acid traps, but it is still good practice to avoid the possibility with your traces. The figure above shows an example of how to correct such issues with those sharp angles and right angles. Let's go to the next point that negatively affects the quality of the signal: the presence of stubs in routing. These are represented as a branch or unused part of the track. The stub effect also causes ringing of the signal. We just discussed that in the last section. In addition, stubs cause reflections due to branches in the signal path, and under certain conditions, each stub can act as an antenna, and that's going to cause interference for our high-speed signals. So it's recommended, if possible, to exclude these stubs from routing, and placing the tracks in series as a single trace is our best option. So you see here in our example, we have rerouted that trace so that it is now in series across those two pads. Okay, And our next point is considering the length of a high-speed track. It should be as short as possible. Depending on the speed rate, there exists a critical length for the track at which it begins to be considered electrically long. In this case, the impact of the track's own capacitance and inductance begins to have a negative impact on the quality of the signal. In general, specifications for high-speed standards describe the maximum allowable lengths for tracks. So it's recommended to place high-speed tracks at the very first stages of routing to ensure that they are the minimal lengths and have no interruptions. Okay, and the last concern we will discuss is with differential pairs routes. So, differential pairs are one of the most popular methods of data transmissions because they are sufficiently protected from outer interferences. It has two main requirements, and they are homogeneity of impedance and its correspondence to the specified impedance in the chip's dataset. So asymmetrical routing of the differential pair leads to the heterogeneity of the impedance, which leads to signal reflections and ringing, which, as we have mentioned several times, reduces the signal quality. So all of the errors that we have discussed are quite common, but they can be easily corrected on an already routed PCB in just a few clicks with the gloss and retrace tools. So let's begin to talk about those tools. We will start by talking about the gloss tool. So right now I will initiate one poll. Okay, so we will talk about the, routing from the first attempt is rarely possible, right? So often we'll route a set of tracks, and when you route the second set, you will change and move some existing tracks, manually drag and dropping things, or with the interactive tracing of other nets. But the resulting routing may have some unnecessary bends and cause the described problems from earlier. So to create clean tracks with minimum number of angles, the PCB editor includes the glossing tool for smoothing already placed tracks. The tool, what it does is it thoroughly analyzes the selected tracks, and it reduces the number of angles, which reduces their length and makes them more accurate overall. The central figure shows the data bus where routing quality can be improved pretty significantly. So it's possible to manually reroute each of those tracks, but that's going to take some time, and it's more convenient to just use the gloss tool here, right? So the tool will automatically improve the geometry in just a few clicks. So you simply select the desired segment, track, or group of tracks, and you select Route, Gloss Selected from the main menu, and that's it. Altium Designer does all the work for you. In the demonstration, I will show you a set of examples of how this tool works on a real PCB in different cases. Now let's consider the retrace tool. During the PCB design process, there can be cases when it's necessary to change the rules for our routing. So, for example, to increase the width for a power net, or to change parameters like the width of the track and the gap between them in a differential pair. Again, for example, when the printed circuit board material has changed, and the tracks need to be reconfigured to match the value of the target impedance. So once the rules are updated, however, all placed tracks are not updated automatically. So here we have a choice again to route the tracks manually, spending our precious time on it, or we can use the retrace tool. So while the gloss tool tries to reduce the total length of the traces and the number of angles, The retrace tool applies the preferred values of widths and gaps from the rules to our existing traces. So with the retrace tool, we can easily reduce and increase the width of a selected set of traces, and even the width and gaps of differential pairs. And again, this works for single and multiple traces simultaneously. So let's switch over to some examples on the board, and let's get started with that.
Okay, so we are now going to switch over to Altium Designer for the practical portion. Let's take a look here at one of our sample projects. So these two projects that we're going to be looking at are included in the sample data set of Concord Pro. So as soon as you install Concord Pro, or if you use Concord Pro on Altium 365, you will have these projects available to you if you want to try this out for yourself. So we look at this trace down here, and we immediately start noticing we have these little areas right here. This doesn't look very great. We have down here as well the same type of little areas. So we want to kind of fix that up a little bit. So here's a little trick. If you select any segment of a trace and you hit tab, it selects the entirety of the trace along the top or along that layer. If I hit it again, it will select the trace across all layers. We just want to select it on this layer, of course, though. So I'm going to select that, and I will go to Route, and I will do Gloss Selected. And we see automatically there, it will apply the gloss tool, and as we mentioned earlier, it will make sure that it will reduce the number of angles for us so that we do not have those interferences there. It will reduce the number of sharp angles there for us. And we're going to do the same thing here for this one. And as you saw here, there are a couple of shortcuts, of course. So you can see route, the U is underlined, so you can do U and then the L. So the shortcut UL, if I select, I can do UL and apply it there as well to that trace. Now let's come over here to a differential pair. We have the same type of situation. We want these to be uniform. We see there's some issues here. We don't want this situation here with these vias. That could cause some signal reflection. It's going to cause some signal ringing. We don't want that there. So we're going to simply select those. And once again, the other shortcut we have here is Control-Alt-G. So if I simply select that, Control-Alt-G, once again, we see right there that that is glossed over, and we have perfect traces right there. So you might be thinking, well, does this only work on single traces or differential pairs? No, you can be working with multiple traces. We have the same type of situation over here. This via kind of got in our way when we were laying down the traces earlier. So I'm going to select this area, and once again, Control-Alt-G, and you see right there, it's going to clean all of that area up. Once again, you can have the same type of, I can do it manually if I want, but, right here, we can see quite simply, I can do it manually, quite nicely, or I can select it and do Control-Alt-G. and have very similar results. It just kind of depends on what you're looking at, right? So there you have it. Those are some of those are a couple of different options we have right there. Coming over to another area over here, we have some very sharp angles right here. We definitely wouldn't want to have this area right here with this sharp angle for no reason. As I mentioned earlier, with the improvements in manufacturing technology, having a right angle isn't the worst thing ever. For the higher speed your design is, the worse the signal reflection. But for lower speed designs, it's not the worst thing. But for here, there's absolutely no need to have this type of situation. So I kind of want to select all of these traces right here. To make it a little bit easier, I'm going to go to the selection filter, and I'm going to disable components right here. And you know what? I'm also going to disable vias. And we see right here, selecting. And once again, Control-Alt-G to make it simple. And we saw all of that get cleared up very quickly. That would have taken me, it would have been quite tedious to fix that myself manually. And we saw I just took a couple seconds making sure I got my components and vias out of the way, just to make it really easy to select everything and gloss it over. So why don't we go and check out another layer now? So I'm going to come down here to this layer, zoom out just a little bit. And you see we have these traces down here. And I'm going to select them. You see, we've attempted to kind of round out these traces a little bit, just to make things a little bit easier, avoid some signal ringing, and what we want to do now is to make that cleaner. So I've selected this now, and actually something we're going to want to do is we're going to want to change the style here, the hugging style. So when you are changing when you're dragging, I can hit tab to pause here and bring up the properties panel, and you can change the hugging style here. So I'm going to change this to rounded, and I'll hit this again, and I'm going to select these. And now I'm going to gloss these. And you see right there, that is a lot better right there. And that saves us a lot of time. You see how much cleaner that is. It makes the track, the minimum distance, as we mentioned earlier. We want to make sure that the distance for all our traces is as short as possible. We have ensured that as well. The fact that these are curved traces, we have made the curves as smooth as possible. As you saw a little bit earlier, they weren't super smooth. Now in Altium Designer 20, we have introduced the ability to route at any angle, and it really improves the ability to lay down your traces and optimize how they are actually placed. Okay, let's see, we have a couple more traces. As I mentioned, we have the any angle routing capability. These were kind of placed really quickly with that functionality, so these are clearly not optimally placed. So I am definitely going to want to clean those up. Once again, shortcut, Control-Alt-G or UL if you would like. You see right there, a lot cleaner, smoother path, and we have the shortest possible distance. We no longer have those sharp angles that we had, little tiny sharp angles that you could see a little bit earlier. And we're going to come over here as well. We see here these are pretty nice. We have this little area right here that we would want to clean up. We could easily just kind of straighten that out if we would like. But I think that there is potentially a shorter path here. So let's check it out. Let's see if there is something the tool could do for us. And in fact, using the any angle routing, the algorithm shows us that you actually have a shorter distance here. In fact, you can go all the way through here, and you have the shortest distance possible here. And as we mentioned earlier, it's really critical when you have these high-speed signals to have the shortest path, so that the inductance and the capacitance don't start interfering with the signal quality. So we have that here, demonstrating to us that even if you have a pretty good laid out path, most of the time there is a way to optimize that path rather easily. Okay, so now we're going to switch over to the Kame FMU to look at the retrace tool. So we're going to start on the top layer, and we are going to start by looking at the design rules. So when we look at a design rule here, we look at this one for a single net, and we see that it is tied to an impedance profile. So the cool thing about impedance profiles is once you make a change to the impedance profile, it's actually going to update this design rule. So this is a really powerful functionality. And I'm going to show you how this is really quickly, how this is done. So I'm going to open up the Layer Stack Manager with DK. So make sure that if you are working with the Layer Stack Manager that you have the Properties panel open. If you haven't worked with impedance profiles before, I recommend you watch the impedance profile webinar. We have it up on resources.altium.com/webinars. We also have it up on YouTube. So we see here, we are going to be working with this impedance profile. As you just saw, I was connected to that design rule. And you see right here, the width is shown to us here. And we are going to change the material here. And when we click this, it opens up our material library, and we are going to change it to this different material here. And you see that as soon as I change the material, it automatically will update the required width here. And it will, if you have, for example, a differential pair, it will also upgrade the required gap. Of course, since this is not a differential pair, there is no gap there for us. But I'm going to save this layer stack here, and I will come back over here. I will go to my design rule, and you will see that things have been updated as necessary for us. So we will come through here. You see on our bottom layer down here, it is the appropriate minimum and preferred width, as we just saw on our layer stack. So I click OK, and I'm going to come down here and select it and go to Route, Retrace, and there we go. It is automatically applied as needed. Come over here and I have this other one. And as we were working earlier, we had the the hugging style set to right. When I start dragging interactively, I can hit tab to pause it, and come over here to change my properties. We have the different hugging styles that can be changed here. When I was working over here on the motherboard, for this area, I changed the hugging style to rounded. Now that I'm working over here, I want to set it back to mixed. I also have the ability to change it in my preferences. If I come to PCB editor interactive routing, I can change that here, as well as changing the effect, the routing gloss effort. So if you want to make it a little bit weaker, you can do that as well. So I am going to come over here, and simply select these two and retrace those as well. Okay, so now that is done. Since it is a differential pair, I always like to try and gloss them, just to make sure. So, you see right here, there was a very slight difference, but the tool did find a shorter path. So I come back to my selection filter and I enable the selection of polygons. And you see here, in Altium Designer 20, you now have a polygon action area. So I'm going to simply select Repour, and right there, I have reported my polygon, and I have the optimal positioning for that differential pair. There. Okay, so from here, what about if I need to change the width of another wire or something? So I'm gonna come over to I just want to change this particular trace. So I'm going to open my design rules again. And I have a rule specifically for the width of this trace. Right. So I'm going to change it to 0.7 as my preferred width. And I'm going to say OK. Select it. And now, once again, when I retrace it, do the same thing I did earlier, polygon, repour. And you can see right there, really quickly, I took care of everything I needed. I got it. I was able to change my rule, apply it as needed, and repour my polygon in a matter of seconds. Okay, now I'm going to go to this other layer. And we see over here, I have this bus, and it's actually a UART bus. And I have some rules for it already. And I actually want to lower the gap in between everything, and I want to as well. I want to reduce the minimum width for everything, so I'm going to reduce the preferred width to 0.1 as well. So I make those two changes, and I come back. I'm just going to set a polygon selection enabled. So I'm going to disable that for 1 second and just select those and quickly retrace. You see how quickly I can make those changes, gloss them over, and lastly, re-enabling polygon selection, repour, and you have completed everything you need to do to make that bus, to decrease the width and gap of that bus. Okay, one last thing to show you. I'm going to go down to the bottom layer, and I had a component over here. I accidentally went into single layer mode. Oh, I went, there we go. Okay, so we have here this component. It was moved slightly, which, a lot of times you have to move a component, and occasionally when you do that, you're going to get some stubs, you're going to get some random little sharp angles, some right corners here. So what I want to do, I'm going to remove the vias selection and the polygon selection here, so I just have tracks, and I'm going to come back out here and simply select the area around it. You see everything is selected as I need, and I will gloss this. So this is the very last thing. I have, once again, repour that polygon, and you see how easy it is when you need to make a last minute change. How often do you need to move a component? You need to do that all the time. And if you need to move it just one tiny little bit, it can cause a huge, a lot of problems. So now you see how easy it is to clean it up, and that's it for the demonstration. We are going to go back to the question and answer section. Thank you for your time, and thank you for attending.